Welcome to this video. We are from Electric Circuit 2 BEJ10403 Courses Group 1 student. We are going to present our assignment about the second order circuit and sinusoidal steady state analysis. My name is So Jia Yi.
Hello, my name is Lim Huang Hong.
My name is Kijo Su.
Now I will present the introduction part. There are two tasks in this work. The objective of this paper is to learn the analysis technique for a given network problem using suitable stimulation approach. The skill we'll learn by us after the assignment is solve the current or voltage response of second order circuit, solve steady state expression, stimulate second order circuit, and steady state current or voltage. We also will learn the skill of demonstrate the second order circuit and steady state analysis.
We have to make sure that in order for us to get the overdamped, critical damp, and underdamped response, the alpha has to be more than the omega naught for overdamped. Both values have to be the same, critical damp, and the alpha has to be less than omega naught for underdamped response. So as you can see that the omega is actually, we have fixed the value as 200. So and the formula is 1 over square root LC. So in order for us to get back 200, the L and C has to be a fixed value, which is 5 milli for both L and C. And since we have fixed the value of L and C for the alpha, which is 1 over 2 RC, we only have to change the value of R so that we can control the value in order for us to achieve overdamped, critical damp, and underdamped easily. So for the overdamped, as you can see, it is the alpha is equals to 1000 and the omega is equals to 200, and then we find both roots value. Alright, so the roots will be using a formula negative alpha plus square root alpha squared minus omega naught squared, and then we got negative 20.2 and negative 1979.8, and then we use the general equation for IT in overdamped response, which is the IS plus A1E ST plus A2E ST. So over here we substitute every thing inside this general equation. So the IS is actually the final value for the current of the whole circuit, which is the 5 amps that we have given in the question. And then for the S, we substitute negative 20.2 as S1 and negative 1979.8 as the S2. And then to find the value of A1 and A2, so what we do over here is basically we take this general equation, we substitute the T as 0, and then we're going to form a first equation. And then we use back the general equation, and then we find the derivative of it. After we find the derivative of it, and then we substitute 0, and we make it equals to the V0, which is the initial capacitor voltage divided by L, to get a second equation. So after that, we solve both of these equations simultaneously, and we're going to get our A1 and A2 value, and then we substitute inside back to the general equation for IT, and this IT will be equals to ILT. So to find the VT, we know that the V is equals to L di over dt. So basically, we just use back the final equation that we got for ILT, and then we differentiate. Alright, we differentiate it, and after that we multiply with the value of L, which is the 5 milli, and then we're going to get our VT value, and this VT value will also equals to the VCT. And for the critical damp, basically the steps are just the same. The only difference is the value of the alpha and the value of the omega will be equals to each other, which is 200. And then the general equation for the IT will also change, which is IS plus bracket A1 plus A2 T bracket E power negative alpha T. And then we repeat back all the steps that we have shown in the overdamped response just now, and we're going to get for our ILT as well as for our VCT equation. And for the next slide is our underdamped value. So for underdamped value, as I mentioned just now, the step is going to be the same. The main thing is now the alpha is less than the omega naught, and then since the alpha is less than the omega naught, we're going to bring in the complex number in, which is to find the roots, right? The equation is going to be a little bit different. We're going to have S1 equals to negative alpha plus minus J omega D. So this J omega D, sorry, the omega D is actually have another formula, which is square root omega naught square minus the alpha square, and then we're going to get 2 complex number, and then the same thing apply. We have another different general equation for the IT in underdamped response, which is the IS plus A1 cos omega D T plus A2 sin omega dt bracket E minus alpha T. So same thing, we substitute everything in, and then we repeat all the steps again. So we're going to get back our ILT and VCT for underdamped response. So as you can see, it might have a little bit longer because it involves trigonometry inside the equation. So now I'm going to show you our simulated circuit using MATLAB Simulink as the simulation tool. So as you can see, at the top it's the overdamped response, at the bottom is the underdamped response, and at the middle is the critical damp response. Okay, so this is what it looks like once we've used the simulator to simulate our circuit. And for the right hand side, it's basically a scope for us to see our response graph. Okay, so all the overdamped, critical damp, underdamped response graph will be shown in the scope. So once we run our circuits, it needs some time to compile. So once the compile is done, and we double click on the display, or you can see the scope, it needs some time to run. So there you go. This is our graph that's been shown by the MATLAB. Okay, for critical dam, under dam, as well as the over dam response. Okay, so over here, as you can see, that it shows whenever the all three graph. Alright, for the top one is actually the graph for the current, and the bottom one is the one for the voltage. And once they comes to time, they will all goes to one final value. And for the current is the 5 amps, which is exactly the same that you given in the question. And the one for the voltage is 0. Okay, so over here we can show if we only want the over dam current graph, we can close the other two graphs to show. This is the over dam, and if we want to show the critical dam, we can just click the critical dam, and for the under dam, we can just open the under dam. So this is all audio. Okay, and same thing goes to the over dam, critical dam, and under dam voltage. We can show everything one by one, just like so. This is the under dam voltage, this is the critical dam voltage, and this is the over dam voltage. So now this is the zoom-in version of the graph. To answer the question in 1D, so we have to focus on this voltage. So the 80% of the voltage value is 0 because 100% 0, so the 80% is also 0. And so we have to find the shortest time on reaching the 80% of the voltage value. So as you can see, this is the blue color one, right? We look at the blue color one. So the blue color one, the shortest time on reaching it is around 0.1 second, as you can see at the bottom here. And for the purple one, time reaching to 0 is around 0.05, and for the yellow color one, or you can see the green color one, it's around 0.2 seconds, which is this about this region. So over here we can conclude that the purple color one, which is the critical dam voltage, has the shortest time on reaching the 80% of the voltage final value, which is at 0.05 seconds. Okay, now we continue back to the slide. Now I'm going to show you for the task 2A. So over here we have to use two types of methods to solve this circuit. So we have chosen the nodal analysis as well as the mesh analysis. So I'm going to show you the nodal analysis first. So the nodal analysis, we have 3 nodes over there, and we have node there with V1, V2 as well as the V3. Okay, and then we form the equation at V1, V2, V3 nodes. Okay, and then we solve it using matrix techniques. Alright, we type in everything into the MATLAB, and then we'll have one kind of a solution, which is we can get the V1 value, V2 value, and the V3 value. So each of this is actually in the rectangular form. Okay, so I'm going to use the V3 in order for us to find the VT. The VT is actually the V3. So we take the V3 value that we get, okay, and then we transform it into the polar form, which will get 56.512 and 48.63 degree volt. Okay, this is the polar form for the VT at the capacitor with a value of the 9 microfarad. So before we actually started every calculation, so we have actually changed all the capacitor and the inductor into the rectangular form, which we use the formula J or WL or J omega L, and for the inductor, and 1 over J omega C for the capacitor. So as you can see, I have used 4 different colors to separate them. Okay, and since we already have the value of V1, V2, and V3, in order for you to get the IA, IB, and IC value, we're actually using the V1 value divided by the ZL1, which is the J ohms. Okay, and then for the IB value, we use the V2 to divide it by the 5 ohms, and the IC, we take the V3 value and then we divide it by the impedance, which is the negative J 11.11 ohm, to get all 3 values of IA, IB, and IC, as well as the VT. And then we use the mesh analysis. So same thing, we convert the all the inductor and the capacitor into impedance form, and then we use mesh analysis. Okay, so the first mesh is actually the IS value, which is the ampere. Okay, because according to the mesh analysis, all right, whenever there is a current value that is shown in the mesh, so that's the value that we're going to use for that loop. Okay, and then we're going to form our second mesh, third mesh, and the fourth mesh. And once we have all 4 mesh analysis equation, okay, since the first mesh analysis with the I1 is already has the value which is 10 ampere. So what we do is we take the second mesh, third mesh, as well as the fourth mesh, and we form into a matrix form as well. And then we use the matrix method to solve it, and we put it into a MATLAB, and then we got the value for the I1, I2, I3, and the I4. So before we continue, alright, so for the IA, IB, and IC, actually we have to use the I1 to minus the I2. So why I1 minus the I2 is basically because the IA is moving downwards, and the first mesh analysis, which follows the direction of the IA, which is going down, alright, but the second mesh, the direction is moving up, so which is the opposite direction. So we're going to use the one that is follow the direction of the IA minus the one that opposite of it. So for IA, we use the I1 minus the I2. For IB, we use I2 minus the I3, and for the IC, we use I3 minus the I4 to get all the values, and all the final value is actually in the polar form. And as you can see, those values is actually the same from which the one we have get it from the nodal analysis. And for the VT, once we get the IC value, alright, we straight away multiply with the impedance negative J 11 ohms, and we get the value of the VT, which is the same thing that we got it from the nodal analysis. So as you can see, this is our simulated circuit. Okay, where this simulated circuit is actually the one we have in our question. Okay, so this measurement over here is actually for current 1, current IB, and current IC, and this one is for the one the VT, because we know that when we connect everything that is across it. Okay, so basically when connect everything that is across it, it's for the voltage. Okay, so let's run the simulator first. So once we run the simulator, we can see that this actually having the same value as we have calculated in method analysis and the nodal analysis. And now I'm going to show you the graph for the current. So as you can see, this is the graph for 3 current. So let me open up this one. Alright, so this blue color is actually the one for the current IA. Okay, and then this is the current IA, and this is current IC. So why we don't put the V over here is actually because, as you can see, if you put all 3 graphs together, this green color line is actually to show the 0 and the y-axis. Okay, so as you can see, the highest amplitude, alright, that's shown over here is actually the 10, which is the I3. So for the voltage, I'm going to show you the voltage. This is the one for voltage. You can see the amplitude is actually more than 60. So if you put everything together, the graphs for the current will be extremely small. Okay, so that's why we separate the current and the voltage.
Now I will present the analysis and discussion part. In analysis of task 1, the formula of omega is 1 over cert LC and is set with 200 plus to obtain overdamped, underdamped, and critical damped response. The value of capacitor C and inductor I is set to 5 millifarad and 5 millihenry respectively. By changing the value of R, the value of alpha can be easily to control and fulfill the requirement of alpha greater than omega, alpha equal to omega, and alpha smaller than omega. The formula of calculating the overdamped response rules is negative alpha plus minus cert alpha squared minus omega squared. For the critical damped response, the formula is negative alpha plus minus cert alpha squared minus omega squared. But since the value of alpha and omega is the same, therefore the roots for the critical damped also can be equal to negative alpha. The underdamped response, the formula for calculating the roots is negative alpha plus minus j omega t, whereas the omega t is equal to cert omega squared minus alpha squared. The above formula is the overdamped response, critical damped response, and the underdamped response. Substitute the value of S1, S2, and alpha into the equation, then substitute t with 0 to form the first simultaneous equation. Next, use the same IT equation that has been substituted by the S1, S2, and alpha, then differentiate it before substitute the t with 0 and make the second simultaneous equation equal to V naught over L. After solving the simultaneous equation and substitute back into the IT equation to get a complete IT equation, since Vt equal to L di per dt, therefore we can obtain the Vt by multiplying the value of L with the derivative of the IT. The Vt equation obtained is also equal to the Vct equation. In analysis of task 2, method used to solve the circuit is nodal and mesh analysis. All sinusoidal current and voltage supply equation has been converted into polar form, and all the inductors and capacitors value are also converted into rectangular form. In mesh analysis, by using Kirchhoff voltage law, in each loop, 4 mesh equations are formed and solved by using matrix method via MATLAB. The Vt value at the capacitor with the value of 9 microfarad can be obtained by multiplying the I4 with the capacitor in polar form. In nodal analysis, by using the Kirchhoff current law at each node, 3 simultaneous equations are formed and solved using matrix method through MATLAB. The Vt value at the capacitor with the value of 9 microfarad is equal to the V3, Ia is equal to V1 to divided by 100 microhenry, Ib is V2 to divided by 5 ohm, and lastly, for Ic is V3 divided by 9 microfarad. In discussion of task 1, while the values of voltage is 0 volt and the current is 5 ampere in steady state, after a long period of time of connecting to the power supply, the inductor will act like a wire. The current is 5 ampere because when the inductor acts like a wire, the current will start to flow to the inductor that acts like a wire. And the charge stored by the capacitor will also flow to the inductor. Since the inductor acts like a wire, there is no resistance on it because the resistance of a wire is equal to 0. Hence, no matter how much current supplied by the current source, it will flow back the exact value back to the current source. In addition, since all the current will only flow into the inductor as well as the charge stored in the capacitor, and therefore the potential difference that has in the capacitor will also become 0. In discussion of task 2, what the value of Ia, Ib, Ic, and Vt shown using MATLAB Simulink as simulator is slightly different than the value of Ia, Ib, Ic, and Vt using manual calculation. The power supply in an AC voltage and current source and the AC power supply will keep changing the value until it reaches its steady state. Therefore, the slightly different in both result is due to the timing that we set using MATLAB Simulink, and also the decimal places that we took for the manual calculation is slightly different than the MATLAB Simulink used.
In question 1, the value of BC and IL for the T larger and equal to 0 is different for overdamped, critical damped, and underdamped. The immediate response graph and combination of all response graphs are plotted by using Simulink in MATLAB. In question 2, the value of Ia, Ib, and Ic is almost same, with using different methods of analysis which mesh analysis and nodal analysis. The graph of the steady current and voltage response also plotted by using Simulink in MATLAB. As you can see, the value of IC calculated by 2 different methods have a little bit different. This situation is due to the raw and raw, which is the difference between an approximate of a number used in computation and its exact value. That's all from us. Thank you for watching this video.